Okay, the next relationship that we'll discuss is one that was investigated by a guy by the name of Avogadro. Interesting to try and say that 10 times quickly. Avogadro, you'll remember, he's the guy that we named that one particular number after. Remember the 6.022 times 10 to the 23rd particles or molecules or atoms in 1 mole of a substance. That number here, we call that Avogadro's number, but he also has a law. And what he did is he looked at the relationship between the volume of a gas and the number of moles of a gas. So we saw Boyle already. This isn't Boyle, this is me. We saw Boyle, and he looked at the relationship between pressure and volume. We looked at Charles. He looked at the relationship between volume and temperature. And now Avogadro, we'll see, looks at the relationship between the volume and the moles of gas. So here he is, Amedeo Avogadro. Isn't he a scary looking guy? Smart though. Anyway, so we've seen relationships between temperature, pressure, and volume already with Boyle and Charles. So how about with the number of moles of gas or the kind of gas? That's interesting. I wonder if you have a different type of gas, whether it will occupy more space. Avogadro explored that, and what his hypothesis said was that equal volume of ideal gases would contain the same number of molecules no matter what kind of gas. Interesting. So if you have a certain volume, it doesn't matter what kind of gas you have, you're going to have the same amount of gas in there, the same number of moles. So the number of molecules in a specific volume of gas is independent of what kind of gas you have. So his law specifically looks at volume, and it looks at the number of moles. And he found again that there's a direct relationship. So if you have a certain volume, say 10, and maybe you have 2 moles of gas. So if you jump your volume to 20, you're going to have, if you double it, then you've got to double this one. You'd have 4 moles of gas in there. So that's his law. It's a direct relationship. If you up the volume, you will also up the moles. Notice that we're maintaining temperature and pressure. So if you keep those the same, then the volume and the number of moles, direct relationship. So this is his law, V1 over N1, V2 over N2. So let's try a question with that. So here I've got a question. I've got 2.55 moles of gas, occupies a volume of 59.5 liters at a certain temperature and pressure. So if I have 7.83 moles of helium, how much volume am I going to need? Let's just look at that quickly. So I've got 2 there and about 7 there. So I'm like tripling things. So I would probably expect my volume to have to triple as well. Let's plug things in and check it out. I should have written this other thing on the side here. I didn't. P1, V1, T1, N1. Was there another one? I think that was all. P2, V2, T2, N2. So pressure we're keeping the same. So V1 was 59.5 liters. V2, well, I didn't know. Temperature, right, that was a wash because it was the same. Then I started with 2.55 moles and I ended with 7.83 moles. So my question was, if I have this many moles to start with, and that's my volume, if I increase the number of moles, then what will the volume increase to? That's my question. So here's my equation. I want to solve for V2. So doing some formula manipulation, V2 is equal to V1 N2 over N1. Again, if you have troubles with that, holler. V2, oh, we don't know that one. V1, 59.5 liters times N2. Again, try not to get mixed up as to which is which. Divided by N1, 2.55 moles. 3 sig figs all around. So I want to determine the sig figs. Break out your trusty calculator. See if I can find mine. Okay, so I have to go 59.5 times 7.83 divide 2.55. 182.7. 182.7 moles cancel, so it'd be liters. Now let's think again. So that was tripling that. So tripling 60 gets about 180. That's about right. Let's check sig figs. I started with 3 all around. I need 3, so it'd be 183 liters. So if you were to increase the number of moles of gas to this, you would need 183 liters, given that the temperature and the pressure remain constant. Now, one interesting thing that some people have done is they've said, okay, let's look at specifically a standard temperature and pressure. Again, that was I forget the exact numbers, but we had a special number for temperature and a special number for pressure. And it turns out that if you have those particular conditions, that if you have 1 mole of gas, it'll occupy 22.4 liters. Doesn't matter what the gas is, it's going to occupy that. It has to be at STP though. So, for example, here if I have 3 moles of a gas, the question would be, what would be the final volume? Notice that the formula is very similar. This would be V1N1, and this would be V2N2. So it's the same formula. So if I wanted to know what the new volume would be, of course it would be triple, right? Because I'm tripling the number of moles, so I would triple the volume. So I'd have 22.4 liters times 3 moles divided by 1 mole. Again, 22.4 times 3 would be about 67.2, I think, close to that, liters. Okay, so that's just one, and that is if the solution or if the gas is at STP. If it's not at STP, then you just use Avogadro's law. V1 over N1 equals V2 over N2. If you have something specifically only at STP, only in those conditions, then you can use just this general rule. 22.4 liters holds 1 mole of gas. Again, remember that that is any gas, so it doesn't matter if you have chlorine gas, or if you have hydrochloric gas, or if you have methane gas. 1 mole of any gas will need 22.4 liters of space at STP. Okay, that is Avogadro's law. Well, next, after this, we'll look at some other relationships between all of the properties.